So numerical solutions, I guess we'll get probably just started with the ideas here. So a numerical solution is going to follow the approach where we need to develop what's called a state equation. So a numerical model requires a state equation that can be integrated through time one step at a time. So the state equation provides the derivative of the state variable, or state variable is temperature. It's the state of the problem is its temperature. So the state equation relates the derivative of temperature to some function of temperature and time. So think about what that means. I'm saying if you give me a moment in time, you give me the temperature of the body that we're looking at, I can compute the change in temperature with time. That's a state equation. So any equation that does that for you qualifies as a state equation. You can use that to develop a numerical model. So let's look at how that plays out. For this example, we have again our same example we've been dealing with. We want to develop a state equation, which is this dt temperature d time is a function of time. We have the ODE already, right? We have gone through the energy balance. Let's say we do exactly the same thing. We get to a point where we have the relationship dt is equal to this. This is what we just derived, right? This is where you need to get to start a numerical problem. So if you can't get to this point, you can't really do the numerical solution. You always need to get to the point of having this state equation that relates these two things. But OK, so I have this. What are my next steps? So first, I'm going to go through here. And just like we did with the conduction problems, I'm going to discretize my domain. My domain is now time. So I need to break up my time window into individual time steps so that I can evaluate the temperature at each of these positions. So we would do that just by saying, time at node j. So we'll use j for our indices in time. Eventually, we'll be combining this with conduction problems. So t at time j is equal to, j minus 1 over m minus 1 times the simulation time, t sim, for j in the range of 1 to m. So m is the number of time steps that I have right down here. That's the number I want to simulate. Again, I want to go from time equals 0 to tm, so I have to divide by m minus 1. And then this is a 1-based indexing, so I'm going to start with j minus 1. So t1 is 0 by the evaluation of that. Tsim is just the total horizon. I think it's fairly clear. So what the state equation is trying to do is I'm going to say, give me some time tj. I'm going to make an evaluation of the derivative at this point, tj. Based on the derivative, which we assume then is this linear function, I can predict my next temperature at tj plus 1. That's entirely what we're trying to do. That's it. We're just evaluate the derivative, project forward, compute the temperature, done. Do the same, then move forward, do the same thing. So you start getting this like linear, piecewise linear function that tells you how temperature is changing with time. Okay. So conceptually, that's it. I think next time what we'll do is get into implementing something called Euler's technique. And then we'll go through, actually, we'll go through a bunch of different options next time. So, OK, thanks, everyone.